Okay, so let's say that we have a roller coaster, essentially, that is released from rest and comes down some kind of cliff, and then onto a horizontal surface, and then it goes around a circular loop, a circular track, like that, and then it goes back onto a horizontal surface. And let's say that the radius of this is h over 3, given how I drew it. So here's the object, and let's say its mass m naught, and it's released from rest, so it comes down, and we want to know when the object is here, what is the normal force of the track on the object. Okay, so what's Fn? So most likely we need to deal with ma equals sum of the forces. Let's see what that looks like. So we could do a free body diagram, and we have Fn pointing upwards and m naught g downwards. So the right-hand side is Fn unknown upwards minus m naught g, and the left-hand side is the ma for circular motion, and so there's an acceleration toward the center, and that acceleration is the unknown speed of the object squared divided by the radius, which is h over 3, so that's the same thing as 3 in the numerator, and then we have m, because that's the acceleration, and we have, therefore, m naught. So it looks like that. So Fn is equal to 3 m naught unknown speed squared over h plus m naught g. So we need to know what this is, and that comes from a different principle. So we're using ma equals F and conservation of energy. We could think of it as work equals delta K as well. So here we have mgh, it's all potential, and then afterwards we're at the bottom, it's all kinetic, actually m naught unknown v squared over 2, and so we actually need v squared here, so we'll solve for v squared, that's 2gh, and so this becomes 3 m naught over h times 2gh plus m naught g, and that is, we'll cancel the h, we'll have 6 m naught g plus m naught g, which is 7 m naught g. So that's the normal force. That's the magnitude of the normal force that way on the cart.